Hello, Assalamualaikum. Good afternoon, everyone. Can you hear me?
Good Doctor. We can hear you.
Okay, great. Thank you. All right. So, welcome to our first, not to say face to face, our first live online class. So, we are in the last week of Ramadan, which is the reason why we're having it like this online. Okay. So, this is our class registered under the code EMM4412 and EMM4416. Um, so I just wanted to remind you, those that maybe have not taken a look at the recorded session from last week. So basically, I just wanted to recap the important items, which are basically the evaluation. We have assignment 1, individual, 20%. Assignment 2, group, 20%. Midterm test, 20%. And final exam, 40%. So as I have mentioned last time, for the first assignment, it was given in that recording, which is last week. The due date. So can you see the slide for the first assignment that I'm showing now? Is it
Can.
okay. I'm worried because sometimes it does not. Okay, so for our first assignment, it is an individual assignment. The due date is on 18th of April 2025, Friday, 5 p.m. And I have actually created a portal for you to submit the assignment on Putra Blast. So there are 10 questions. So you're just assigned one question each. And based on the questions that you assigned, you have to write a comprehensive maximum 15 pages. So maximum, okay, not minimum. Okay, maximum 15 pages report on the topic. And the file submitted must be in PDF. Of course, we are talking about technical reports. So all facts must be cited, and all figures and tables taken from other sources must be cited as well in their title, as per what method that you are using for your thesis writing, FYP thesis writing. And of course, it must have a list of references in the end, and the references that were cited in the text. What does it mean? It means that you do not put all the references that you have read throughout when you prepare the report. You only included the references that you cited in, let's say, table, figures, or text, or the facts inside the report. And of course, all tables and figures must be numbered and mentioned in text. What does it mean? It means that basically you should have like figure 1, figure 2, figure 3, for example, and then you just do not put in figure and tables. You also mention it inside the paragraph. Figure 1 is showing blah, 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 blah. Okay, so you have to basically explain the figure and tables that you put in. So as I mentioned, there are 10 questions. Okay, 10 questions. So this is question 1 to 5. And now we have questions 6 to 10. And I have already assigned to you which questions that you have to answer. And based on the registration, I think Kartik have just registered. So Kartik, I think I will give you question number 2. Okay, so I will also include or update this table later on. So basically, this particular semester up until now, we have 15% in class. Yep. Okay, then that's it. As a reminder for the first assignment. So there is a saying that the work actually expand according to the time that you dedicated to it. Okay, so please try, although I've given you the due date to be on 18th of April, try to do it even before Raya. You can actually just submit your assignment in the portal before then if you have the time. Okay, so do not wait at the last minute. So now we are going into, oh, sorry, before that, do you have any questions about the first assignment? Any questions? If not, then okay, I would assume there is no question then. So no. Okay, so let's move on to our subject for today. Isn't something else. Um, okay, so today we are going into the second chapter, whereby in the first chapter it is basically a simple introduction to what is advanced material engineering. So now we are going into the topic, our first material, which is ceramic. So as I mentioned before, in material engineering that you have learned in your first year, think first semester, basically most of the topic inside there covers metals, and maybe a little bit of ceramic and polymers, which is just like one chapter on both ceramic and polymers. But the rest actually belong to metals because most of the structural equipment, everything mostly is made of metals. But in advanced engineering materials, this particular subject, we're trying to basically explore other type of materials that is out there. And ceramic is basically one of the main materials that exists on the face of this earth. So you have metals, you have ceramic, you have polymers, and then you also have composite, according to some study. Okay, but maybe some other books they just say metals, ceramic, and polymers, and composite actually belong to the subset of the materials under each category. If let's say if the composite is mostly made of metal matrix, then it falls under metal. If the matrix is made of ceramic, it falls under ceramic. If the matrix is made out of polymer, it falls under the polymer category. But there are also some books that basically registered composite as another category of material because of its behavior. So um, we can go either way, it doesn't matter. We also have one chapter on composite in our subject. Later on, we will go to that. But first, ceramic. Um, so what is ceramic? Things that you should basically, even if you have forgotten whatever that I told you in this particular semester, even until the end of life, you should remember that ceramic have these three characteristics. One, ceramic is very good under compression. So meaning
Doktor,
that, yep.
ni tak bergerak, slide tak bergerak.
Oh, okay. So you still on the first page. Saya try share balik. Hmm, okay. So now you should be able to see the page on the main characteristic of ceramics. I'm making it full screen. Then I move to the applications. Did it change?
Tak.
Tak juga. Okay, then we try another way. Okay, I just share the whole screen lah. Okay, so now I'm opening the ceramic slides. And full screen, I move to main characteristic of ceramics. Dah, dia play ke?
Dia tukar dah.
Okay.
Cepat dah.
All right, thank you so much. All right, so as I mentioned just now, the three main things that you should remember about ceramics is that it is very good under compression. So not talking about its behavior under tensile or under bending property, not talking only about compression. So it is the best material that will give the best performance under compression. And another main characteristic of ceramic is that it also have a very, very, very high melting temperature. So meaning that if you put ceramic in a situation where there is a fire, everything will melt except for ceramic. So it have very high melting temperature. And we will go through what are the range of melting temperature. Of course, it also have a melting temperature, but the value is very, very high. Okay, so we will go through the values later. And then it is also corrosion resistance, meaning that you can take a ceramic material and put it beside salt water and it will not change in properties in 100 years, 200 years. It is not like metal and it is not like a polymer, whereby a metal, it is usually susceptible to corrosion, and for a polymer, it is susceptible to corrosion by chemical reaction, but not ceramic. Ceramic have a very high corrosion resistance. Okay, so those are the three important characteristics of ceramic. All ceramic have these three characteristics. And you have to remember this point. It is very good under compression, good strength under compression, high melting temperature, and high corrosion resistance. So there are many applications to ceramics in this current world. So basically, ceramic is started as a structural material, meaning that when you wanted to build a house or any foundation of buildings, you need bricks, and brick is basically a ceramic category material. And then from construction, then as the evolution of our knowledge continues, then people started to find other application for ceramics. So now, if you look at the functional classification of ceramics based on function, so you can use it in electrical situation. Previously, people think that ceramics is not conductive, but with a certain tweak in elements that you put in processes, you can make it into a semiconductor. Okay, or you can use it as it is as an insulator, but the function can be used in electrical components. And then we can also add in some metal elements inside the ceramics to turn it into magnetic material. And then, of course, glass belongs to a ceramic category, so it falls under optical. And then, in a car itself, there are also parts of it that is made of ceramics. That is why automotive is also a function where you use ceramics there. And then, of course, in mechanical, we use it as a cutting tool, abrasives. And then in biomedical, basically, we are also made of ceramic. Our bone, hydroxyapatite. Our bone is made of out of an element called hydroxyapatite. And hydroxyapatite itself is under the category of ceramics. So basically, if you take a human bone and you grind it, and then you do some processes to compact it into, let's say, a pellet, that pellet is made of ceramic. Okay, so not going to grim, don't find any human bones and do these processes. And then we have, of course, the construction, the bricks, and then there are also other application where we use ceramics nowadays. You can also use it in armor material, defense application, sensors, nuclear, metals processing. And then because it is corrosion resistance, usually we use it in chemical application, uh, and then of course domestic is talking about household items. Or most of your plates that your mothers love is made of ceramic material, the whitewares. Okay, and of course now we can also have the jug kettle also can be made of ceramics as well. So there are many diverse application of ceramics, but it is all based on the three characteristics that it have, as I mentioned just now. Okay, so I told you that it have a very high melting point. So just to show that this is example of but I guess you can also see my arrows, but a pointer would be better, I guess. So these are examples of materials, and then these are examples of their melting point. So basically, if you wanted to compare the melting point of, let's say, um, tin silver copper alloys is around 227 degrees Celsius. And the melting point of, let's say, aluminium, I think it is around 700 degrees Celsius, around that range. Um, but most of the metals will not withstand 1000 degrees Celsius. Most of it will melt below 1000 degrees Celsius. But when we look at the melting point of ceramics, it is very, very high, more than 1000 degrees Celsius. If you look at polymers, polymers actually perform much worse compared to metals. Let's say the melting point of polymers would be, have you tried to put in hot water inside a polymer jug that is not supposed to hold hot water? It will deform, meaning that there are some softening of the polymeric material that take place in that particular situation, and the hot water temperature is maybe around 100 degrees Celsius. So the melting point of polymers is very low, around maybe 200 degrees Celsius. Not talking about the advanced polymeric materials nowadays. It's talking about common polymeric materials. But even if you engineered the polymeric materials, definitely it will not be able to go up to this temperature. Okay, so ceramic, it have very, very high melting point, more than 1000 degree Celsius. So always when we wanted to process ceramic materials, we have to make sure that the crucible that we use have to go higher than 1000 degrees Celsius. Okay, so this is the melting point, but luckily for processing, we will see later on, we will not go through the process where we have to melt it properly. I mean, we have to melt it fully for this, for the subsequent process of producing a component. We will just up to a certain temperature, and then we go for and then it will just sorry, it will just bind itself and then produce a component. Okay, but these are the melting point. Of course, the thermal expansion coefficient will change depend on the material itself. And another important property for ceramic is that it have very high hardness value compared to metal and polymers. So meaning that it have a very low wear rate. Okay, so meaning that if you grind it, it will not wear off as fast as metal and also polymers. So that is why it is the material that is being used to grind other material into shape. So high hardness and also very high melting point. And then when you look at the properties that it have, so the density will change according to the process, which we will go through later on when we talk about the processes to produce components from ceramic. But basically, you should know that the density is not fixed for a composite. It depends on the process that it goes through. And of course, that also influence all the other properties. But just to show the difference between the tensile strength, the flexural strength, and the compressive strength. Because as I mentioned just now at the start, composite perform very good in compression. So if you wanted to compare the properties, you can see that, for example, alumina, tensile strength is only 207 megapascal. Flexible strength is 552 megapascal. But when you look at the compressive strength, it is 3025 megapascal. It is more than double, triple, quadruple, I don't know, after 5 times, 6 times, multiple. I don't know. But basically, it it's really high compared to the tensile strength and the flexible strength properties. So that is why a ceramic is basically used in a situation where it have to perform in the compressive state. Okay, and then of course the Young's modulus, okay lah, not that bad if you want to compare to metals. Of course, fracture toughness, it is very brittle, very low fracture toughness. Basically, if let's say you take a metal and then you take a ceramic, you wanted to uh, test the brittleness of it, and of course ceramic will fail miserably because it is a very brittle material, but it have a high wear resistant, it is high in compressive strength, and it also have a very high melting point. So look at the good things only for ceramics. All right, so when we talk about ceramic material, usually, basically in each material category, there are many ways to classify it. To say that, okay, this belongs to this group of material, that belongs to that group of material. For ceramic, one way to classify it is by the application. So we can have glasses as the first category, whereby glass is different from others in the sense that it is amorphous. We know that ceramic have ionic structure, as what you have learned in year one first semester. It's different in the way that it is ionic, but it is amorphous when it solidifies. So that is why glass is glass, because once it solidifies, it stays in an amorphous state. And because it stays in the amorphous state, there is no grain boundaries. So when there is no grain boundaries, then the light will not be scattered at the grains and it will go through the material because it is amorphous, no grain boundaries. So without scattering, it just goes through. That is why glass can be see-through. That gives the characteristic of a glass. So because it is see-through, then glass can be used for optical. It can also be used to reinforce composite, for example, the fiberglass composite. And then it can be used to hold things. And you have seen it usually in your house, hold items, because it is see-through. You put things in, you can see it from outside what is inside the container. Okay. So glass belongs to one classification. And then the next classification is clay products. So when we talk about clay products, so clay is a naturally found material from Earth. Usually, there is a specific type of soil that you call as clay. Okay, so that soil will then be mixed with water and of course nowadays some other elements, and then you will shape it into whatever shape that you want, like the um, maybe uh, what is that called in bahasa English? I can't remember. Water jug, for example, the previously made water jug from some um, centuries ago. Okay, and of course, whiteware also can belong to the clay products because it can be made out of that soil. Okay, and then and sometimes for structural we also can categorize it under clay products. If let's say you are making bricks, that brick is also made of soil, plus of course some aggregate, something else, pebbles, and then you compact it into whatever shape that you want, square of course for bricks, and then you fire it up and then you use it to stack up and build houses. That can also be categorized under clay product. And then we have refractories. What is refractories? Refractories are a situation where the ceramics is being used due to its ability to withstand high temperature. And when ceramics is used in this application, then it falls under the category of refractories. For example, just now we talk about bricks in household items to make a house, so it belongs under clay products. But now, if you made bricks and you build a furnace, then it falls under the refractory classification. So basically, this is talking about the lining inside the furnace that you use to melt things. So the furnace shouldn't melt before the material. How to ensure that? To ensure that you need to use ceramics. That is the only thing that can withstand that very high temperature. So ceramics would be the first line of defense inside and outside, sometimes inside only, inside of the furnace. So that whatever that is inside will melt, but the ceramic, but the furnace itself will not, will not melt. Okay, so whenever it is being used to melt stuff, and usually furnaces, the lining, whatever component of ceramic that you put in there, it belongs under refractories. And then abrasive. Abrasive is something that you are familiar with. Of course, we are all mechanical, so mechanical works with sandpapers. We cut stuff using abrasives, and we polish stuff using abrasives. So it is being used mostly to shape things or to grind something. Okay, and then cements. So cements is different from others in the sense that the solidification process depends on the chemical reaction between the elements inside the cement. For example, for glasses, clay product, refractories, abrasives, whatever that you form, in order for that to change into a solid state, involves heat, meaning that you have to put it into a furnace that will basically remove all the moisture from the component and make the particles solidify or just stick to each other, and ta-da, you have a component. But for cements, usually you use it in structural materials, for example, to build that very high MRT tower. um, you definitely cannot build a furnace big enough to produce those components. So we use cement. So cement, in the sense, you put all the elements that you should have, and then you add in water, and then you shape it into the shape that it should be, and then you leave it, and it will harden because of the chemical reaction between the water and the elements inside the cement that will make it harden. Okay, so that is why cement falls under another classification. And then the last classification would be advanced ceramics. So basically, all glasses, clay products, refractories, abrasive cements have been out there forever. Okay, but then now we have advanced ceramics, whereby as the technology evolve, as we find new information, then we can produce ceramic material with unique capabilities. For example, uh, maybe you can produce ceramic with piezoelectric properties, or you can produce ceramic with magnetic properties that is not natural, and then you can use that for certain application that is suitable. And those kind of things belong under advanced ceramics. Okay, so that is classification of ceramic material based on the application. And now we are going to take a look at the formation. So now that we know we have all the different type of ceramic material classification, but now the next question is, how are we going to produce a component from it? Because we know that ceramic is not like metals. Metals, you can cast it, because it have acceptable melting point, which is maybe around 600, 700 degrees Celsius. And you have ceramic that have very high melting point that can be the container of that heat and can hold um, the metal as it melts, right? And then after that, you can pour it into what is acuan in bahasa Inggeris? Whatever container. Oh, you can pour it into a die, and then that die will take a certain shape. And then as it solidify, you take out the metal from the die, and then you can actually lathe it or do whatever processes that you want with it to produce the final component. But that is not workable with ceramic. For one, it have a very, very high melting point. Let's say around 2,000 degrees Celsius just now. If you wanted to heat up the ceramic to 2,000 degrees Celsius, even the furnace will melt because the furnace itself is also made of ceramic. Okay, so it is basically not possible to melt it. But let's say by chance you are able to melt the ceramic material into liquid, and then you then put it into a die. I wonder what kind of material would that be, but you put it into a die and solidify it. Now what's next? Because you know that the ceramic is very, very brittle. So meaning that if you wanted to shape it into a different shape, then as you try to cut it, it will just break into pieces. Okay? Either it will break into pieces or the cutter will break into pieces because it is very hard, it is wear resistant, and it is very brittle. Okay, so it will not give you the shape that you want. So you cannot go through the normal, you can say the usual path of producing a metal component. So for ceramic, it is very different. So now we are going to look at the three different types of ceramic fabrication method. So the first type belongs fully to glass because glass behaves differently. As I said, it is amorphous. And then after this, we will go into particulate forming and then finally the cementation, because I mentioned to you that cement behaves differently whereby it solidifies as it reacts with water, a chemical reaction. Okay, so first we go through glass forming. Okay, so when we talk about glass forming, so what is glass? Glass, you know, I'm sure by now you have seen several videos, or if you have not, you should, whereby you can take a look of how they produce glasswares. So glass is unique in the way that as you expose it to high temperature, it will melt and change into different viscosity. So meaning that as you expose it to, let's say, 1,000 degrees Celsius, then from a very hard material, it will start to soften. And then once it's softened, then as you increase the temperature, 1,300 degrees Celsius, then the viscosity will become higher. So when I said the viscosity is higher, it means that it becomes more watery. If the viscosity is lower, it is more like dodol, a sort of thing. So meaning that it is fluid, but it is not spreading well. Sample like that, yeah, maybe. So viscosity, when I said is very high, meaning that it becomes more watery like. Okay, so as you increase the heat that it is exposed to, then the glass will becomes higher and higher and higher viscous, and in the end it will be like water spilling all over. So for glass forming process, what people usually do is that people take this globe of glass and then they expose it to heat until the viscosity is sufficient enough or is possible to be handled. Okay, because it has softened, but it is not like going all over the place. It still stays in one place, but it is soft. So meaning that it will follow whatever shape that you want. So that is where we have glass blowing using a physical person that blow and shape it into whatever shape that is required, which is mostly used for artistic pieces. But now we talk about manufacturing process. So blowing of glass bottles, it is a process whereby you heat it and becomes a gob, put it into a Parisian mold, and then you press it. It becomes a glass in this shape, and then you move it to another place, a suspended Parisian. Then it have another die with a bigger dimension, and now you put in compressed air, like automatically blow it, and it will just expand and then fill in the cavity. Okay, and then you can open up the die and take it out, and then let it cool down to room temperature. Hardens. Okay, so there are also pressing, whereby the gob of glass is then being pressed in a mold made of steel with graphite lining. I would expect you to memorize this, but you should just know the process. Okay. So pressing for plates and other cheap glasses, you just use pressure to the mold, and then tada, it is ready. Or for fiber optics, you use fiber drawing, whereby this is using the gravity effect as the melted glass flow down, then there is a wind up of the fiberglass to just make it sure that it goes to another process that actually hardens the fiber. Okay, then we also have the normal big glass, like usually for, let's say, structures like the front part of your car, or your vanity glass also goes through this process. So in this process, you have the molten glass, and then you have effect of gravity, and then it floats on the liquid tip, because you need to cover the other part with something. If you don't, that will just be see-through. But if you wanted to use it as a vanity glass forever, you can just coat it with something else, or you can just use this to suspend. Doesn't matter. We can go through grinding later on to remove whatever that is required. So basically, you just float it on whatever solution that you want, and it comes out, and then you go through the annealing furnace to remove the stress from the glass, because glass, as it solidify, um, it have some stress trapped inside. If the stress is too much, how does it affect the material? It will become harder, yes, but it is also more prone to brittle failure. So that is why we have the annealing process in some processes afterwards, to remove the stress from the component. And then once you have removed the stress, then you can cut it safely into whatever size that you want. Okay, so let's go to the bottom of the glass structure. So glass is usually made of silicon dioxide. Okay, so basically meaning that silica, yeah, we know that ceramic usually have anion, cation. That is a must. So meaning that one element have the positive attributes, another element have a negative attributes, and then as the cation and anion merge, then it becomes ceramic. And glass is made of silicon dioxide, or the other name is quartz. Okay, so glass is most of the time non-crystalline. It is amorphous. But of course, you can change glass into ceramic as you add in some other elements. Okay, so glass can also be made into crystalline, but you have to modify the process, and you have to add in something else, other impurities inside, to make sure that it is prone to form the grain boundaries. Okay, so there are many type of glass. So basically, to produce glass, you can simply go to the side of the beach, take the sand that is made of silica, and then you take that sand and then you expose it to very high temperature, then it will become glass. Okay, so that's why glass is very famous, because you can produce glass from the sand at beach. Okay, so another name for silica is also quartz. Quartz is also another name for it, and quartz is usually being used when the silica is in a crystalline state. So meaning that it is in an orderly form. We call it as quartz. But when it is in a non-crystalline state, usually we call it as glass. Okay? So it is the same thing. It's just that if it is organized, you call it as quartz. If it is not, you call it as glass. And then commonly for glass, it likes to be in an amorphous state. Okay? Because you would add in impurities in glass to achieve that. Okay, now it's opposite. Okay, so sorry. So for glass, you add in impurities so that it becomes amorphous. But silicon dioxide on its own is prone to become a crystalline structure. And we call it as quartz. Okay, so there are many, many different types of glass depending on the type of impurities that you add in. Okay, so let's take a look at the glass properties. When it is in crystalline form, when it is in amorphous form. Okay, so this is the line. Let's say now it is in liquid form, and this is the end where it is in solid form. Okay, so for glass, now it have impurities, so it actually disrupts the formation of the crystalline phase, so it becomes amorphous. So as it cools down, then it becomes super cool liquid, meaning that the viscosity reduced. This is very high viscosity, and this is going lower viscosity, whereas the lower temperature going as the temperature lowers down, and then now it belongs to the super cool liquid. So but still it is flowable and changeable, soft, very soft material. And then once it hit the glass transition temperature, poof, everything turned into solid. So it becomes amorphous solid. Okay, so that is glass. How about when it is in its pure state without any impurities? Now, also from the liquid state, very high viscosity, and then once it reach the melting point, or if you look from the other side, solidification point, then suddenly the volume will shrink down very fast because it rearrange itself into whatever order of crystal structure that you should have. Then it solidifies. Okay, so what is the difference? Difference is that one, for the amorphous part, where glasses with impurities, it does not crystallize. So there is no grain boundaries. And the change is very linear, like this. Also, because no grain boundaries, it is also transparent. Okay, then it becomes solid at the glass transition point. But for crystalline material, it crystallizes at the melting point or the solidification point, and then it basically have a sudden change in volume at this particular temperature. What does it mean? It means that it will shrink down. So you see this is a higher specific volume and this is lower specific volume. So once it jump down, then it becomes crystalline solid, and meaning that it shrink a lot from the original state. So what does it mean? It also means that there are also some you can say defects that can happen during this state once it change from liquid form into the crystalline form. Okay, so it does have an effect on the component later on, right? So that is the difference. Okay, so we know that for glass, the viscosity decreases with temperature. So this is the viscosity and this is temperature. So as you heat it up, then it becomes more and more viscous, meaning that it is more and more watery like. So different type of glass have different viscosity. So this is all talking about different type of glass. So what is the difference? Here is the formula. For example, soda lime glass, which is this one, consists of 70% silicon dioxide, and then you have natrium dioxide and calcium oxide. And then for borosilicate, is it Pyrex? Yeah, Pyrex. You have 13% boron dioxide, 3.5% natrium oxide, 2.5% aluminium dioxide, and the rest is, of course, silicon dioxide. And then Vicor, you have 96% silicon dioxide, 4% boron oxide. And then fused silica, you have more than 99.5% silicon dioxide. So all of these have silicon dioxide at different percentages, and you have different type of impurities. And these impurities actually affect the viscosity change of the material. So meaning that as you expose it to temperature, the rate of the change in the viscosity would change according to the percentage of the silicon dioxide and the type of impurities and the percentage of the impurities that you put in to the glass. Okay, and but the most important thing is that you have to take note from this graph is that there is a certain working range. So meaning that if it falls in this range of viscosity, then you can use whatever processing to form it into whatever that you want, whatever shape that you want. And then this is the common annealing point or annealing temperature that we use in the process to remove the stress from the component. And at this particular point of viscosity, yeah, it is still soft, but it is prone to break if you you wanted to change the shape at this point of time. Okay, so at this kind of viscosity, yes, it is soft, but you can also break it because it is transitioning into solid. And this is the annealing point, this is the working range, and this is the, when it falls under this viscosity, we just say that it is already fully melted. Okay, so basically you cannot do anything with the glass at this point because it is like water, unless you wanted to use a process that you wanted it to be in that particular form. Okay, so this is the change of viscosity with temperature, and it actually determines the processes that you will carry out to form the component. Okay, so another thing we should know about glass is that there are basically heat treatments that you can do. As I mentioned, you can use annealing. What is the purpose of annealing? To remove the internal stress caused by uneven cooling. Okay, as you shape the glass, definitely the outer part will cool down first compared to the inner part, and that gives some sort of like difference in terms of the stress distribution and might cause some defects later on. So annealing is used to remove the internal stress that is caused by this uneven cooling. You want to remove the stress. And then there is another type of heat treatment where you purposely do this to induce stress. Just now you wanted to remove the problem, but now you wanted to give a problem so that it can solve another problem. Okay, so that is tempering. So tempering is bad when you wanted to make sure that the outer part or the surface of the glass is always in a state of compression. Why you want it to be in a state of compression? Because we know that glass is very brittle. Just one scratch can be a very big catastrophic effect on ceramics. So what we wanted to do that is that using the tempering process, we wanted to put the surface of the glass into compression so that if there is any crack forming on top of this surface, then because of the compression, it will just push the scratch together or push the crack together, then it does not propagate throughout the component, just to stop small cracks so that it becomes stronger. Okay, so what is the process of tempering? So you have the hot material and then you cool it very fast on the outer part so that the outer part will become cool faster compared to the inner part of the component. Of course, to carry out tempering, the glass itself need to have a certain thickness to it so that when you force the outer part to cool down, the inner part is still hot. So the idea is that once everything cools down to room temperature, the outer part will have the compression property while the inner part will have the tension property. And that stop crack from propagating. Okay, so stop it actually suppress the crack. But what happens when the crack actually propagate to the inner part where it's supposed to have tension? Then fails lah. Too late already. So because once it reach into the tension part, then it just force the crack to become even bigger. So tempering is used to stop the crack or slow down the crack propagation only at the surface. Okay, and then of course nowadays for car windshield, for example, we have laminated glass, whereby you have two unit glass and then it is sandwiched with a layer of polymer to hold it together so that once the glass breaks, does not into your face. It will just stay there as a not one piece, but still in place. Okay, is for safety reason, right? Now we go into the ceramic processes with powders. Okay, so of course, first, in order to use this method, you need to synthesize the ceramic first in powder form. So to do this, we use ball milling, blending, spray drying of powders using processing additives. So spray drying is that you mix the slurry powder in the slurry with some solution and then you spray it. As it cools down in the air, it becomes fine powders. The same method that people use to produce milk powders. Okay, the same method. And then once you have it in powder form, then you shape it into whatever shape that you want using whatever pressing technique or slip casting or tape casting, which we will go through later. And then you use this shape process to consolidate it into a dense monolithic object. Then after you shape it, then you wanted to make sure that this shape stays and it can be handled. So you use heat to consolidate it into a dense monolithic object using sintering or firing process. Expose it to heat. And then after that, it is hardened. Now you take that component and then it can go through secondary processing. But the secondary processing for ceramic is not similar to the secondary processing of metals or polymers. The secondary process can only be very surface mild process. You cannot then, I wanted to cut this square into triangle. Now you are just making a big problem for yourself. Or I wanted to cut this square into a star-shaped component. That is an even bigger problem that you're trying to do that. Okay, the only thing that you can do is that this is a square component, but I wanted to just trim off the edges to make it a little bit more fillet. That is possible. Okay, so you can only use a secondary process that is very minor, like some grinding, very minor cutting, polishing, or you wanted to coat it with something. Okay, then it is possible as a secondary process for a ceramic component. And then after that, you have the final ceramic product. Okay, so when we talk about powders, so it can go through all of these methods. It can go through slip casting, compaction, tape casting, extrusion, or injection molding. And we are going to go through that detail now. Okay, so it falls under particulate forming when the ceramic is in powder form. Okay, for example, now you already have these ceramic powders that you have obtained through a grinding process or milling process. And then you then screen it into whatever size particle that you want, because different particle size will give you different properties as well. Not only different element. There are a lot of things in ceramic that influence the properties. Okay. Then after you have screened it into whatever desired particle size that you want to process, then you can mix it with a plasticizer, or you can mix it with any other binder, just to bind, to hold the particle together. And then usually at this state, it will be like a plasticine. And then you can then play like Play-Doh using the extrusion process to produce whatever shape that you want, and then you can cut it, okay, to whatever size. Then you can extrude it into round, not hollow, round rod or square shape, whatever that makes sense, like plasticine, exactly like Play-Doh. And then after that, you cut it, and then you take that, and then you put it into a furnace to dry it, and then increase the temperature. Some call it as firing, to so that it hardens now into the shape that you want. And for ceramic, as it goes through all of this process, there is a change in dimension, because it is prone to shrink as uh, it goes through this heating process. For example, at this stage, when you extrude it, maybe the size of the block, let's say 20 mm, 20 mm, 30 mm. So width, height, length, 20, 20, 30. But then as you fire it and it becomes hardened, it will change into 15.5, 15.5, 20. The dimension change. Why it changed? It changed because of the binder. Just now, when you wanted to turn it into Play-Doh, that particle, the swan particle, is being mixed with the binder. And during the firing process, the binder will evaporate and leave you with just the ceramic particles. So it shrinks because of that. So in the hydroplastic forming process, you have to take note the amount of, let's say, this binding agent that you put in. You don't want to put in too much binding agent, because then the shrinkage would be too much. But you cannot put too less of a binding agent, because then it will break just during the extrusion process. It have to be a balance, so that the size definitely will change, but hopefully it does not change much. So that is also something that you have to take into account when we wanted to produce a ceramic component. So this is another method for particulate forming. So just now again, you have the powders. You screen it into whatever particle size that you want. Then you mix it with the binder. And in this particular solution, most of the time we use water for this state of binder. So there are many types of binder. For slip casting, usually we use water. And of course, we mix in with other binders as well. And then you should know that for this method, it is now not like plasticine. It is more like a slurry. Um, Porridge, maybe? A very, um, not a very viscous porridge. Quite a viscous porridge, yeah. Like watery like. Okay, so what happens is that in this particular method, now you should have a dye. And then you pour in, as I mentioned, pour, meaning that it is very viscous. You pour in the solution, and then if you let it dry, meaning that the dye will absorb all the binders out and leave you with that shape that you want, that consists mostly of the ceramic powders. And then you take that green ceramic, we call it as green ceramic because now it is still a shape. It is according to the shape that you want. But if you crush it like this with your hand, it will change shape. Meaning that it is still something that can change shape. Very soft. Okay, so we call this as green ceramic. And at this state, there are still some binder exists inside the ceramic. Okay, so it is still powder to powder binder. So the powder does not diffuse yet with each other. Okay, so we call this as green ceramic. We also sometimes call it as green product. Uh, as you see the word green in front, you know that this is the component made of ceramic that have not gone through sintering or firing, meaning that it is not exposed to the fire or heat yet. Okay, so it is just simply dried component. Okay, so this is if you wanted to produce a solid component made of ceramic. But if let's say you wanted to produce a hollow component, you can also use this process. But now you do not wait until everything, all the binders have been absorbed. So you pour the solution or the slip into the mold and then just stir, like put it, you can, yeah, usually we just move it around and then pour it out. And then pour in another solution inside the dye and then just move it around and pour it out until you get the layers that you want, the thickness. And then you open up the dye and take it out. So it is much more difficult to handle this hollow component shape compared to the solid component shape, of course, right? So again, we call this as green ceramic. At this point, again, I can just crush it with my bare hands. It is still not strong. It have not gone through firing. And then once you take these pieces and then you dry it, how to dry it? Usually there are many methods. Sometimes we just leave it in a room so that more binder will dissipate out from the ceramic, but it is not hardened yet. It's just dry off. And then we take this component maybe the day after and put it inside the furnace. Now you ramp up the heat up to maybe 1400 or 1200 degrees Celsius, which is not sufficient temperature for things to melt, but sufficient enough for the powder to combine with another powder. And then after that process, you have the solid ceramic powder that when you hold, definitely you cannot crush it with your bare hands unless you're Superman. or your Hulk. So no normal person can crush a ceramic with their bare hands after firing process. Okay, so what is the purpose of drying and firing separately? As I mentioned, the volume of the component will shrink as the binder is removed from the component. So once it is in a green state, there are still binders inside. Then you dry it off, just leave it in room temperature or in low temperature furnace. So remove binder, then it will continue to shrink. And then as you fire it, ultimately removing all the binder, then it will shrink to the final shape. So the drying and firing ultimately will shrink the component, but it now happens in stages. Once it happens in stages, what does it mean? It means that you give time for the stress to flow out from the component. So it's not like you force it to shrink down so fast that it will crack. So by doing this in stages, you remove the possibility of the component to simply crack. If there is any cracking, crack formation on the surface of your component through this process, then you just have to scrap it and then mill it again into powder and then start the process from the start. Because if there is any crack formation, then we know that that component definitely will die a miserable death when you started to use it. Okay, because ceramic is very brittle. Any scratches or any cracks on the surface would mean a catastrophic failure for the component once you use it. Okay, so porcelain. Okay, porcelain is a type of clay. So going back to the classification, so for the classification of ceramics, just now we went through by the application, and under the clay product, we have the whitewares, the structure bricks, and then we can also have porcelain inside. Okay, so it is made of clay and cowlite. Cowlinite is the name of the clay, but usually we just call it as clay. And then, of course, if you use 100% clay, it is possible. But if you want to make it cheaper, you put in quartz, or you want it to have certain properties, you put in quartz. Of course, finely ground quartz. You call it as a filler to fill in the space. And then we also have a fluxing agent, which is also called as feldspar. So there's a fluxing agent have a very low melting point, well, compared to all the ceramic category. Um, that is why it is called as fluxing agent. It is also made out of ceramic category material. So sometimes it is made of aluminosilicates plus K plus, natrium plus calcium plus. So it is all types of fluxing agent only. And upon firing, it will form low melting temperature glass. So what is the purpose of the fluxing agent? To just keep everything together. Okay, so porcelain usually consists of these three things: clay, filler, which is quartz, and example can be other fillers as well, and the fluxing agent, feldspar. So clay, what gives clay its properties? What differentiate clay from the tanah gambut that you use to tanah gambut means that the soil that you use to plant trees. Can I take that soil and just produce pottery from that? I cannot. Because clay is different, whereby if you zoom in to look at the structure, the clay is basically like pieces of particles that when you put in water in with mixed with this clay, the layered particles will just move around, which gives it the properties that is possible for you to use to produce these products. So that is why a clay soil, it is also made of soil, and the tanah gambut or tanah laterite, I mean, it is something that you learn maybe in high school, the different type of soil. Okay, so each soil have its own different properties. One is suitable to plant trees, one is suitable to use as a pottery product, clay is used as a pottery product, and it happens so because of these layers properties of the clay. Okay, so that is why when you put in water inside, then the clay particle can move, slide all over each other. It becomes a hydroplastic material. And then this clay, you mix it with feldspar, you mix it with, what is that? Okay. Yeah, filler, the quartz. And once you mix it with water, then you shape it into whatever shape that you want. Okay, you can just Google down and take a look at any pottery lesson and you see that how they shape it into whatever shape that you want. And then you take that and you just leave it, maybe for 1 day or 2 day, or just leave it in the furnace at very low temperature as a drying stage. So basically, the process of drying is to remove the water and slowly. So it will just move from the wet body, then becomes partially dry and then completely dry. And it have to happen slowly, because if you dry it too fast, then the component will warp, crack because of the non-uniform shrinkage. And then after it have dried off, then you take that component and you put it inside the furnace for firing process. And during this process, it happens at a heat treatment between 900 to 1400 degrees Celsius. So meaning that for drying, you can do this at a lower temperature. Anything lower than this, it can be categorized as drying. And then during the firing stage, now during drying stage, it is still soft. So meaning that I can just make a shape or indentation or just club it together as I want. It will change according to whatever pressure that I put in. Then firing, the purpose is to hold things together. And during firing for porcelain, there is another process called vitrification. So what does vitrification means? It means that just now the fluxing agent that you put in, it have a very low temperature and you form a liquid glass. And clay will also melt and flow combined with the fluxing agent, and it will flow between the silicon dioxide particles, whereby the silicon dioxide is the quartz. So quartz will not melt during the firing process. Only the clay and the fluxing agent will change into semi-liquid form and flow through and hold things together. Okay? And there will also be some parts that becomes like a glassy stage. So that is porcelain formation. And then now we go into, this is more like powder metallurgy, whereby again, it also falls under the category of particulate forming. Okay, so we can use this for both clay and non-clay compositions. What happens is that now you have a powder, you put a little bit of binder. You don't want it to be very dry. You also don't want it to be very wet. So binder is just enough to hold everything in place. Not similar to the porcelain method just now. Okay, so this is powder metallurgy. So you put the binder into the plus the powder, and so that it is, let's say, like less than it is actually not even to the state where it is like Play-Doh. It is less than that. Okay. Then the powder, so then you see that it is still in powder, but with the binder, the powder stick to each other. Okay, then you just throw everything inside the pressure, inside a mold, and then there are many ways to apply the pressure. So now you shape it using pressure method. The normal situation is the uniaxial compression, whereby you can simply use the instrument machine in our lab, put into a die, maybe a 20 mm diameter die, pour in the powder plus binder, and then you have like uh, the head of the tensile machine now compacting from one direction. So as it compact from one direction, that is why the name is uniaxial. I didn't put the direction. Okay. So uniaxial means the compaction happens in one direction only. So you compact it, and then it becomes like a coin shape that you can practically remove from the die. So the binder is just to hold the powder so that after the compacting process, it is sufficient to hold the powder together that you can actually handle it and remove it from the die. So that is the amount of binder that you should put in for this method, powder methodology. Okay, so to apply the pressure, just now I mentioned uniaxial compression. There are also isostatic compression. Isostatic, we know that it basically means pressure from all direction. Okay, so for this particular method, you put in the powder with the binder together inside maybe a rubber envelope, and then you apply pressure from all direction into the shape that you want. Okay, so you can basically produce a more complex shape using the isostatic compression. For uniaxial, simple square, simple cylinder would be possible. Let's say I wanted to make a bunny shape, then maybe I better use this isostatic compression. Okay, once you have pressed it into the shape that you want, then you remove it from the envelope. Ta-da! Whatever shape that you have. Okay, so another method is that you press it with heat, because for the uniaxial here and the isostatic here, all of this is to produce the green component, meaning that once you take it out from the die, it have to go through drying and then firing. Then it becomes solid. But for hot pressing, now as you press, you apply heat as well. So you press with heat, and once you take it out from the die, it is stronger. But still, most of the situation, it still have to go through the firing stage. Because how high can the heat go if you use the tools? But at least it makes the component more stronger to be handled for the subsequent process. So that is hot pressing. Again, it is also in uniaxial direction pressing, but now you have the environment of heat being applied to it at the same time. And then with isostatic and heat combined, now it becomes hot isostatic pressing. The same idea, you put it into the envelope, now made of something else, then you apply the pressure together with heat. So hot isostatic pressing. But again, once you take out from the die, you still have to go through the firing stage. But at least now it is easier to be handled because it is harder compared to the green product. But most of the time in the industry, we do not use the hot isostatic pressing and the hot pressing plus heat because it is too much for the machine itself. Okay, and it also costly. So most of the time they use uniaxial compression or isostatic compression. Okay, what happens during sintering, or some call it as firing? So what happens is that the powder particles, this is in original shape. Then as you expose it to heat, remove the binder. At the same time, you'll see neck formation between the particles. Expose it to more heat. So these are the grain boundaries. And then expose it to more heat, then it will just merge, but still you have pores in the middle of it. So this is where the pores come from. So the one thing that differentiate between ceramics and metals and polymers is the ability of the ceramic to form pores. There are higher possibility for ceramic to form pores because of this process of the firing or sintering process. Okay, so if you zoom in, so this is example of aluminum oxide powder sintered at 1700 degrees Celsius for 6 minutes, and you see that this is a hardened component, but this is pores. So previously, pores is something that you cannot run away from with this kind of method to produce component using powders, because there is no way for you to like melt it because the temperature is too much. But you can expose it to a temperature that is high enough for the necking process to happen and the powders to consolidate with each other. Okay, so most of the time when we produce component using this method of powder formation, we need to measure the pore size, the pore shape, the pore amount, so that we know the properties that it will have later on, or how it will influence the properties of the component later on. Okay. Previously, people treat pores as something bad, um, but now there are also some application where we wanted it to have pores because we wanted to use it to screen out something, for example. All right, so we want it to have some pores. So this is another method using the powder method, whereby now again your powder mixed with the binder, but it have to be more viscous because you wanted to use to just pour it into the slip sauce, and as it flows, you have the daughter blade here to control the length, and then you have the warm air source here to dry it off, and then you can reel it up. And this is usually used for uh, parts in integrated circuits and capacitors, very thin ceramics, so that you can roll it up. Okay, so this is another method to produce components from ceramic using powders. Okay, so we have gone through glass forming, we have gone through particulate forming. We now go to the last stage, which is cementation. So as I mentioned, cementation is different to glass and particulate forming, because glass and particulate, you form it into the shape because you combine it with some binder, or you heat it up. In the sense of glass, you heat it up, it change in terms of viscosity, and then as it cools down, it becomes a certain shape that you want. For particulate, now powder plus binder, and then you shape it into the shape that you want, you dry it off, then you sinter it or you heat it up, then you have the component that you want. Both of these process involves heat. But for cementation, you have the powders, you have the chemical plus that you put in water. Then it reacts chemically and then it hardens up. So that differentiate the cementation fabrication method. So usually the chemical reaction take place when you mix it with water, and then using this cementation process, you can form big rigid structure also with complex shape. And the hardening process depends on the hydration, which is the complex chemical reaction involving water and cement particles. So that is cementation, very simple. You mix it with water and it chemically reacts, heat up, evaporate all the water, becomes hardened. Okay, so that is cement. So now this is showing that, for example, you have one type of material, which is silicon nitride, and then you proceed to process it using different techniques. One using slip casting technique, one using reaction bonding technique, one using hot pressing technique to produce the same dimension component. The compressive strength and the flexural strength will still differ because the rate or the amount of binder that you put in will be different. The rate of drying would be different. The rate of sintering would be different, or the firing would be different. And then here you apply pressure. Here you use gravity, a lot of binder, so weaker. Um, so all of those things influence the property of the final product. So meaning that if we wanted to produce a component made of ceramic, there are many, many things that we need to study to make sure that we produce a component with the strength that is required. This is just to show that same material, different technique, very big difference in terms of its property. Okay, just now I mentioned that porosity is also something that you cannot run away from when you produce ceramic, especially using the um, powder method, the one that you involve powder. And even for the cementation process, if you look peer to your maybe no, no, this is usually covered with something else. But if you peer right to the cement slab itself, sometimes you'll see porosity. Okay, so it is, since it is something that you cannot run away from, so you need to learn how to reduce it or how to increase it through the different processes parameter, and you also need to analyze it. So pores, it can be interconnected or it can be closed pores. So what does it mean by interconnected pores? It means that, let's say I have a slab of material in front of me and it have pores. Interconnected pores is that it means that if, let's say, I pour water on the top here, then it can actually merge out from the bottom side because the pores is connected to each other. So the water can flow from top to bottom. So that is what it meant by interconnected pores. But if it is a closed pores, so meaning that the pores is isolated from each other, maybe there is definitely a wall in between it. So if you pour water on top, it will not go down because it is not connected. And the porosity inside a component, you cannot basically say, I wanted to have only interconnected pores in this component and I only want closed pores in this component. So usually it exists together. It's just that you have more interconnected pores or you have more closed pores. But of course, with technology nowadays, you can actually control it to have all or mostly interconnected, all closed pores. Not talking about the current technology, talking about the common situation where the porosity exists, can be a mix of interconnected and closed pores. So basically, you need a formula to measure what is the amount of porosity that the component have. First, you wanted to know the total amount of porosity. And then next, you wanted to know out of this total amount of porosity, what is the amount of porosity that is interconnected or closed. So there will be formula for that. But I think here I only show the porosity for apparent porosity and the true porosity. So apparent is simply uh, estimation of the pores that it should have, but the true porosity is the actual pores that it have, and it is interconnected and and closed pores. I'm not sure. Yeah, and then once you have this calculation, apparent porosity, bulk density, true porosity, then you can use. I didn't show, unfortunately, in the first slide on how to calculate the percentage of the closed pores from these values. But basically, you can take a look at this example here, shows how to use the equation. Okay, so you have any problem with this example, you can let me know later. So you can take a look. So next, so that is the basic theory of what you should know about ceramics. Now you have known everything that you should know about ceramics, at least the important stuff. Okay, so now we'll have activities. So since we are having this online, we are not in class, so we cannot have this real time. But I hope that you can use the time that we have left, another 30 minutes after this, or the class hours tomorrow, to complete this first activity and the second activity. Okay, so for the first activity, we will learn about ceramic powder synthesis. Okay, so this will be group work whereby, well, there are only 15 of you in this class. So you basically know each other, I think, and you can communicate with your friends offline. So you choose your own group members. But as I mentioned here, in the sad situation where you cannot find group members, I allow a group of one person for this activity, seeing that we are in the online situation. Okay, so it's good if you have a member so that you won't be alone. Okay, so there are few methods here. Sol gel method, solid state reaction, chemical vapor deposition, precipitation method, hydrothermal synthesis. So definitely one group will get one title. So now next stage is in our WhatsApp group. You can find your group members and tell me in that WhatsApp group together. Team 1, what is the name plus what is the name? Choose sol gel method. So the next group can only choose other method. You cannot pick sol gel method anymore. Once all groups have covered these 5 methods, then the following, maybe group number 6, can then again choose sol gel method. Is it okay? Is it clear? Can we do this, let's say, directly after I end this online class? Okay. So first come, first serve. So we start with the first group, then you choose whatever method you want. The second group can choose another method. And then we go, covered all 5 method. And then the sixth group can again choose the method that he or she wants. Okay, we'll try to settle it this afternoon, this evening. Okay, then what you should do once you have this method. So I wanted you to study the assigned method that covers these 4 items. 1, what is the processing steps involved? Next, what are the key parameters? Then what are the advantages and limitations? Then the application in the industries. Which industry is being used for, what type of component that you use this to produce, etc., etc. And all of this information should be presented in only a 5 minutes PowerPoint presentation. Okay, so only 5 minutes, please, not more than this. Okay, you can take turns to talk, doesn't matter. All right, what I wanted to know that it is only 5 minutes. Okay, so please include the visuals and the key takeaways and the case studies in that 5 minutes from these four items. And the due date I've given to you 11 April 2025, 5 p.m. But if you can finish this tomorrow, I already opened up the system for you to submit your assignment. Do not wait. This will not be marked, but the knowledge that you share will be will be imparted to your friends and it will be included in your midterm exam. Okay, so once you have prepared your presentation, then uh, your recorded video, you can share this on the Putra Blast to submit. And then don't forget to also share it in our WhatsApp group so that other groups can also see your videos because they will need to answer questions based on your PowerPoint presentation. Okay? So when I said PowerPoint presentation, it is not simply a PowerPoint. You need to present it. That's why I said the 5 minutes PowerPoint presentation. Okay? The video. All right. So share the video on Putra Blast to submit your assignment and in our WhatsApp group so that others can see. Okay. The due date is 11th of April, 2025, 5 p.m. That is the first activity. That is group activity. Next, we have individual activity. So now we are going to go into, just now it is the method. Now it is going to the industry. So it is like a virtual company visit and report. So you can choose one company. Okay, again, first come, first serve. Okay, so if let's say the student number one says he or she wants Kyocera, then the next have to choose another company. And then once complete all four, then the fifth one can choose Kyocera again. All right. So these four companies originate from, of course, it is an international company. It originates from these countries, and before it expands into other countries as well. And then these companies is specifically dedicated for certain application or certain type of product. Okay. And then when you visit the company website or YouTube videos or research papers, I wanted you to focus only on the type of advanced ceramics produced, the manufacturing techniques used, the industries that it served, and the innovation and latest research. So, does it mean that you have to take a look at everything to come up with this? No. Maybe you just take a look at one YouTube video or you just take a look at one site of the company website because I just need you to write 1 to 2 page report. You don't have to make a very extensive study for this, okay? I wanted you to put into the report, one, the company background, two, the key ceramic materials and the applications, and then the latest innovation or trends, and then what did you learn once you go through all of this information, and one main key takeaway from their research or findings. Okay, only 1 to 2 page report, okay? Not more than that. And again, if it is interesting, this knowledge might also appear in your midterm exam. So, for the part to submit, again, the due date is 11 April 2025, 5 p.m. Same due date as the activity number one. So, you can use the time today or tomorrow to complete these assignments. And don't forget to upload it in Putra Blast and also to share it in the WhatsApp group so that others can also read your report and of course to also see the quality of your report. Okay, so you are in the final year, final semester. You are nearly fully engineer now. So your report should reflect the engineer that you are going to be. Okay, so that's it. That is it from me for today. Do you have any questions so far? So any question?
Tak ada.
Doktor nak confirm
Okay.
sekali.
Ya, boleh?
Activity 2 tu individual ke group? Individual eh?
Yeah, activity 2, individual.
Okay, thank you,
Activity
Doctor.
1, group. Yeah.
Okay, thank you.
So, yeah, welcome. So, in the first recorded class, I already shown you few method that you can choose to find information. Maybe you wanted to start from there. Once you wanted to complete activity 1, activity 2. Okay? So if there is no other question, that is it for today. So for tomorrow, there is no class, there is no recorded video, but please use the time to complete activity 1 and also activity 2. Because um, as we go on with the subsequent chapters, you should expect that we will have this kind of activities as well. Okay? So do not wait until the last minute to complete everything. Okay, so that's it for me today. Thank you so much for your participation, and I'll see you guys in the physical class after Hari Raya holiday. Thank you so much.
Thank you,
Yes,
Doctor.
thank you, madam. Thank you,
Okay.
doctor.
Thank you, Doctor.
Thank you, Dada.
Thank you, Ada.